Welcome to The Explainer. Today we're tackling a question that, well, it trips up a lot of developers. It's that feeling you get when you're training a neural network and you just know something's wrong. You feel like your model's lost and you just wish you had a map to see where the heck it is. So this all kicks off with a really common question you see on places like Stack Overflow. Someone's training their model, right? But the loss just isn't budging like it should. And they're thinking, okay, how can I see what's going on? I want to visualize the loss landscape and figure out if I'm stuck in some bad minimum or a saddle point. I mean, that sounds totally reasonable, doesn't it?
Well, here's the catch. That mental picture we all have, the one with the rolling hills and deep valleys, the one we call the loss landscape, it turns out that picture isn't just an oversimplification. It can actually be seriously misleading.
And one commenter, Andres Dake, just nails it. He points out that you're not dealing with 2 or 3 dimensions you can sketch on a piece of paper. Nope. A modern neural net, it could have millions, heck, billions of parameters. And every single one of those parameters is its own dimension.
So that is the world our model is actually living in. It's this vast, hyperdimensional space. And here's the takeaway. You just can't use your normal, everyday 3D intuition here. It completely breaks down. That map we wanted to see, it's literally impossible for our brains to even imagine.
Another user puts it even more directly. They said you're basically blind, just feeling your way through this bizarre, high-dimensional maze. And that's just how it is. So that's the big question, right? If we can't see the map, how in the world are we supposed to find our way? Well, we need tools. We can't use our eyes, so we need something else. And our first tool, it's kind of like a compass. It can't show you the whole map, no way. But what it can do is tell you which way is down, right from where you're standing. And that tool is called the directional derivative.
Okay, now you've probably heard a lot about the gradient, right? That's the vector that points you in the direction of the steepest uphill climb. But this directional derivative thing is different, and that's what's cool about it. It's not a vector, it's just a single number, a scalar, and it tells you the slope in any direction you decide to look. Think of it like taking just one tiny slice out of the whole slope to see what it looks like.
So in practice, it's super simple. You pick a direction, you check the directional derivative, and if the number's positive, that way is uphill. If it's negative, it's downhill. That's it. And this is how we start to, poke around this invisible space. We can start to feel out the terrain, one direction at a time.
But okay, knowing the slope isn't everything. Imagine you're at the bottom of a really wide, flat valley, or maybe on top of a long, flat ridge. The slope might be almost zero in a bunch of directions, so our little compass isn't going to be much help there. We need to understand something more. We need to understand the shape of the land, its curvature.
And that brings us to our second tool. To figure out curvature, we use something called the Hessian vector product, or HVP for short. And if the directional derivative is our compass, you can think of the HVP as our sonar. It sends out a ping in a certain direction, and it tells us not just what the slope is, but how the slope itself is changing. And that's what tells you about the curvature.
Now, I know what you're thinking. Hessian vector product sounds super complicated and computationally expensive. And you'd think it would be, but here's the wild part. Some recent research shows that with modern libraries like JAX or PyTorch, calculating an HVP is actually surprisingly cheap. We're talking only about 2 to 4 times longer than it takes to calculate a plain old gradient. That is a total game changer.
Okay, so let's recap. We've got our toolkit now, right? We have a compass, the directional derivative, to tell us about slope. And we have sonar, the HVP, to tell us about curvature. With these 2 things, we can finally stop trying to picture simple 3D hills and start tackling some really wild navigation challenges in some truly mind-boggling spaces.
All right, check this out. This comes from a research paper where they're solving a differential equation. Now, that sounds complicated, but you can just think of it as an optimization problem in, get this, an infinite dimensional space. Yeah, infinite. Now, look at the images on the left. This is what happens when you try to solve it with a simple, naive approach. It completely fails. It just diverges into total chaos. But now, look at the right. This is with a technique called preconditioning, which uses all that juicy curvature info from our HVP sonar. And look at it. It just smoothly, beautifully finds its way to the right answer.
And the data, the raw numbers, they tell the exact same story. Just look at these plots. See that red line shooting off the chart? That's the error for the simple method. It just explodes. It's completely and utterly lost. But then look at the blue line. That's our smarter, preconditioned method. The error just steadily drops, step by step by step. It knows exactly where it's going.
So what's the secret sauce here? Why is the difference so dramatic? Well, it all boils down to using that curvature information to take much smarter steps.
See, without understanding the curvature, our steps are blind. It's like you might see a gentle slope ahead and decide to take a huge leap, but you don't realize you're on the edge of a cliff. You're just reacting to the ground right under your feet, and it can send you flying off into nowhere. The whole process just becomes unstable.
But preconditioning changes the game. It uses that HVP information to resize our steps. It's like it's telling the optimizer, whoa, hold on, this direction is super curvy and steep, so take a tiny, careful step here. But hey, that direction over there, it's nice and flat. You can take a big, confident stride over there. And it's that control that lets us make steady, reliable progress.
Okay, so let's pull all of this together. What's the big takeaway from all this? I mean, we started with a pretty simple question, but where have we ended up?
Well, we started out wanting a map, a nice 3D picture of the landscape. And we learned pretty quickly that's just the wrong way to think. The real first step is to accept that we're basically blind navigators in this bizarre, high-dimensional universe. But, and this is the important part, we are not helpless. We have this amazing toolkit, a compass in our directional derivatives, and a sonar in our Hessian vector products. And with those tools, we can find our way and even solve problems that seemed totally impossible before.
And that kind of leaves us with one last thing to think about, doesn't it? This whole landscape metaphor is just one example of how our simple, everyday intuition can totally fail us in the world of AI. It really makes you wonder, right? What other easy, comfortable ideas from our 3D world are actually holding us back, preventing us from finding that next huge breakthrough?